Okay, thank you for the nice introduction. Today, I will talk about how we can use light and sound to implement a recurrence operator and how we can extend its memory and also train it. So to start, to give a brief recap, I will explain the physical process in which we base our project on, which is Brion scattering. This is a scattering process where two optical modes are coupled via one acoustic mode, and this can happen in two different processes, either an anti-Stokes process or a Stokes process, depending on the direction of the acoustic wave. And what is interesting also about this process is that it's easy to get into the stimulated regime. And this happens in the following way. If we start with a pump and a seat, and the seat is downshifted by the acoustic resonance frequency of your material, they are counterpropagating, and when they meet, they will form a beating intensity pattern. And then because of electrostriction, they will generate an acoustic wave. Then the pump can scatter off from this acoustic wave, and the scattered light will fall again into this Stokes frequency. So you have the two optical waves reinforcing the acoustic, and then the pump and the acoustic wave reinforcing the Stokes. And this closes the loop, and this makes this process very proficient. It can also be treated as a third-order nonlinear optical effect. And we use this effect to make a recurrent operator, which we call audio, in the following manner. This is our scheme. We start with a highly nonlinear fiber, which is good for getting both light, but also these acoustic waves. And into the fiber, we'll send two sequences of pulses. On one side, we have the data pulses, which are encoded in amplitude, but they might as well be encoded in phase or polarization. Birgit gave a talk yesterday showing all the different degrees of freedom which we have studied. And on the other side, we have the control sequence. These are high power pulses which help us mediate our Brion scatter interaction. So to start the recurrent operation, we send these pulses one by one into the fiber. So they meet, and because this is a coherent process, we can transfer the information from the input data into the acoustic wave. And because this process is not 100% efficient, we will see an output from our fiber. Then in the next step, the story is a bit different because we have, again, the interaction between the data input and the control pulse. But now we have the state from the acoustic wave from the previous interaction. So then this output should depend on our previous input. And we can do this again for the next pair of pulses. And ideally, we should do this many, many times. But as we know, recurrent neural networks tend to very easily forget. And I can also show this scheme if you're familiar with recurrent neural networks unfolded in time. And what is interesting about our implementation is that depending on the spacing between the pulses, I forgot to mention we're using 1 nanosecond pulses, but depending on the spacing between the pulses, if they are shorter than the length of your fiber, you can have multiple interactions in the fiber, and one can interpret this as having different recurrent layers. All right, that's the playground that we have, but we're interested in knowing if we actually have a connection or not between these pulses to see if the recurrence is there. Sorry. So we go back to this representation, and what we will do is monitor the outputs of our network depending on an input, for example. So in this case, showing if we change the first input, we will track how the second output changes, and this is what we observe for 3 pulses. And here we do see, for example, like the second output does see an influence from the previous pulse, for example. And to make our lives easier, we define a quantity called the dynamic range, which is just this slope times 100, so it's closer to a percentage. And to define if we have a connection or not, we check with a reference case, so without the acoustic interaction turned on, and then we see that if we have plus or minus 1% dynamic range, we have a connection. And for room temperature, we saw that this connection persists for 10 nanoseconds, but if we go to the cryogenic case, we can extend the acoustic lifetime, and we can also extend the duration of our connection. So if we want to process, we can see how far we can get. This sort of representation is a bit poor. If we want to do more pulses, we just take the dynamic range, and then we can get a sort of plot like this, where we can see the full connectivity of our network. Here I'm showing like different spacings between the pulses, and also I'm showing the case for the cryogenic case and the room temperature. And we just see here, for example, in the cryogenic case, for very close spacing, we got up to 20 connections, whereas in the room temperature case, we got a very inhomogeneous connectivity, and we also didn't get even 10 connections. Also, as we go farther in time, as we separate the pulses, we see like these connections start to fade away already in the room temperature case, but here in the cryogenic case, we're still at 15 connections. Okay. We have a sort of idea on how we can see this, if we have a connection or not, but it would be nice if we could actually change the connection as well. And for this, we need to train our network. And this is a project in which I worked with my student, Niklas. And the first thing that we thought about is, okay, we want to know like which are the knobs that we can control in our experiments. The first thing that, so the parameters that we should train. The first thing that we thought about is the power of the control pulses, but we didn't want to go this way because we want to keep this as low power as possible. And for the parameter that we actually chose, we got this idea from a project that I was working with my colleague Olivia, where we were implementing optoacoustic memory, and we were working on storing this QPSK constellation, and we saw that we can retrieve the constellation with the Brilliant process. And what is interesting is that the phase of the readout information depends on two parameters. One is the spacing between when do you write the information and when do you recover it, but also the detuning from the acoustic resonance. So if we change the detuning, we see that we can cover the whole 2 pi phase space. So this detuning is a parameter that we will choose to train our system. And I'm putting here an asterisk because we will send a different detuning for each pulse. The next thing is to have a task that we can train our system on. So we came up with this ABC pattern recognition task, and the idea is the following. We have a sequence of 4 pulses on the inputs. The first 3 will be modulated with 3 different amplitude levels, either A, B, C. And so we have 3 pulses with 3 levels, so we have 27 different classes to classify. And we let these pulses interact, and the idea is that just by measuring the amplitude of the last pulse, we should be able to tell what was the pattern that we sent in the first 3 data pulses, because they're connected via the acoustic waves. This is how this looks like if you plot the amplitude of the pulses for the 27 different cases, for the first pulse, second pulse, third pulse, and last pulse. This is the reference case, and once we turn on the interaction, we do see how this states start to split one by one. And here we already start to see different amplitude levels for the 27 different patterns. And so we can see this, but we want to have a metric of how good we're performing. So for this, we employ a random forest classifier, and this should just tell us how good we're able to separate this 27 different patterns. Okay. The next thing is to have an algorithm so for this we went with this SPSA algorithm because it allows us to change all the parameters simultaneously. It's very quick. If you go to the lab, each epoch takes a short amount of time, and we were looking for this to reduce the experimental time of the training to fight drift, for example. And we also do this in situ. So we measure the output of our system and then change the parameters accordingly, and then slowly it should converge. And then for the loss function, we came up with this idea of the overlap loss function. So you can see here, for example, in this case, we're performing with 50% accuracy because for some classes, we have the same amplitudes. So ideally, one should have as little overlap between different classes. So this is what we want to minimize, the overlap between the classes. So after the training, we should be able to separate them or open this I, for example. These are like some results that we got. We do see the loss going down once we start the experiment. We see the setup learning some different frequency mismatches. And here we do see the evolution of the 27 different classes after every epoch. We see at the beginning there's a very small range, so all the 27 different levels are very close to each other, but then over time it opens up. We can also see this from the random forest classifier. At the beginning, we get a 39% classification accuracy, but then after training, we got to 92.6%. Also, because this process doesn't require the long-term recurrence, at room temperature, we also got a nice number after training, 84.4%. Okay, with this as a summary, what I've shown you is that we implemented a recurrent operator based on stimulated Boolean scattering. So it's coherent, frequency sensitive, and is programmable. I've shown how the training can increase its performance, but also as a take-home message is that these acoustic waves also open up a new playground for implementing different computing architectures. With this, I would like to thank my group, especially my supervisor, Birgit Stiller, and of course my student, Niklas Braven, who were working on this project. And I would like to thank you for your attention.
So, is there someone behind me?
No, but they will pass it.
Right. So, very, very cool system. You said something about, so the obvious thing was to change the power of the control pulses.
Mm-hmm.
And I understand that you have this other elegant solution, which is neat, but why did you want to change that? That seems like such a natural knob that would provide more control over the process.
Yeah. I mean, we were thinking, we already have a crested, so we cannot argue so much about power efficiency, but we thought about, okay, what is the limit that we can push our system on with, like, let's say, like a power budget that we have. Like, imagine, like, this situation. So, of course, if you put more power in the control pulses, you increase the amplitude of the acoustic waves, so you can increase whatever information that you store, and hopefully will pass down, like, for later operations. But we were also interested in like, knowing or like exploring other dynamics from a system, let's say. And we saw this from the frequency tuning.
Okay, so you're currently operating at the lowest control pulse energy that you can still do this at? Is that the situation?
That's the idea, yeah.
Okay, all right, that's very clear. Thanks.
Thank you. Thanks a lot for the great talk.
Mm-hmm.
Is there a specific motivation why you use the SA algorithm? And could you expand a bit more on the idea behind this algorithm?
I think the motivation, as we said, it was mostly like because we want to do this experimentally, so we want to reduce the amount of time that we take to train our system. And this SPSA algorithm, what it does is like perturbates all your parameters simultaneously. So we saw this as a great opportunity to optimize like our setup, or like our training loop, let's say.
So when you say you perturbate all the parameters simultaneously, like this is some sort of multiplex perturbation, or is this stochastic? You're trying a random perturbation and it brings you?
It is stochastic. So you perturbate everything, but like in different directions.
Okay, so it's a zeroth order method where you look at all parameters.
Yes, I think.
Okay, thank you. So let's take the
Jesus.